Hi, and welcome to Microfluidics 1. Today we are going to talk about diffusion. To understand what diffusion is, we better start with an example. On the right-hand side, you can see a Petri dish, and inside the Petri dish, there's some liquid. And the purplish point in the center of the Petri dish is a crystal that slowly starts to dissolve within the liquid. And if we look now how the crystal propagates within the liquid, we can see that it slowly moves in a circular shape from the center of the crystal in all directions of the Petri dish. And this effect that we can make visible with this crystal is called diffusion. To understand this effect, we first have to get to know the governing equations and understand the principle of diffusive mass transport. And then based on these equations, we will have a look at a simplified problem, and we will use these equations to determine the mass flow induced by diffusive effects. Okay, then let's start with a theoretical consideration. And on the right-hand side, you can see a state 1, which consists of a gas 1 and a gas 2 that are separated by a membrane, and both gases are inside the same container. What would you expect happens if you remove the barrier between the two gases? So if you look and you can still separate the gases, you would see that they slowly start to mix, starting from the interface at the start here. And after a certain time, you will have a perfect mixture of gas 1 and 2, which is described here in state 2. So in general, we know that this happened, and I guess it's somehow intuitive to you as well that they wouldn't stay separated. But what is the driving force for this mixing phenomena? To understand this, we have to come back to one of your first lectures where we took a closer look on gases, and we did a microscopic view of them. If you remember it, we stated in these lectures that gases basically are small particles that move randomly in different directions. And this movement is induced by thermal effects and is called Brownian motion. If we now remove the barrier between the two gases, the particles will spread randomly across the complete container. And this finally ends up in the perfect mixture that we just observed on the macroscopic scale. The driving force is, as often in these types of systems, the entropy, which usually tends to be maximized. To describe diffusive transport, you can use the diffusion coefficient D, and it basically describes the solute's interaction with the solvent. So usually, if you look at liquids, you have one liquid and there are particles inside at different concentrations. The solute in this case would be the particles that move through the liquid, and the solvent would obviously be the liquid. For gases, diffusion coefficient can be described by the Arrhenius equation. So you have a maximal diffusion coefficient D0 times the exponential function of minus the activation energy divided by the gas constant times the temperature. So this means the higher the temperature, the smaller the value in the exponential function. So if the temperature gets really high, this second term goes to the value 1, and then you get the maximum diffusion coefficient as diffusion coefficient. For liquids, you can model the diffusion coefficient by the Stokes-Einstein equation, which is given here. So the diffusion coefficient equals to the Boltzmann constant times the temperature divided by 6p eta r, where r is the radius of your particle and eta the viscosity of your liquid. And the idea behind this equation is that you consider the movement of the particles within the liquid based on the drag force. So this means that it depends on the size of your particle. The bigger the particle, the lower the diffusion, the slower the diffusion. And it obviously also depends on the viscosity. The higher the viscosity, the slower your particle movement. If we now return to our first example with the two gases separated within a container, you would expect that there, at the start at least, there is a flow of oxygen from the 100% concentration area in direction of the carbon dioxide. And obviously, if it's a perfect mixture, the carbon dioxide has also moved on into the right direction to fully fill the container equally. So how can we now determine this fluxes in opposite directions? And for this, you can use Fick's first law, which is given here on the left-hand side. So you have the flux, the diffusive flux, which is equal to minus the diffusion coefficient times the gradient of the concentration. And this makes somehow sense if you think about our situation here. At the start, that we have a 0 concentration of O2 on the left-hand side, and we have a 100% concentration of O2 on the right-hand side. And the driving force for the diffusive flux is now the concentration difference from 100% to 0%. And obviously, the closer the concentrations are to each other, so the smaller the difference on the right-hand side, the slower the diffusive flux gets. So for this equation, we only consider stationary effects. So we don't really consider temporal changes. And if you're interested in the temporal development, you can use Fick's second law, which is written here on the left-hand side. So you have the temporal concentration difference on the left-hand side, which equals to the minus the gradient of the flux plus a source term. And the gradient of the flux is the gradient of the concentration. This is basically Fick's first law. And this is why you can write it like this: D times delta C plus the source or sink term. And the idea of this equation is quite simple. So if you look at a control volume, so let's just consider the CO2 area on the right-hand side. If you look at this control volume, the temporal change of CO2 will basically be the CO2 leaving this control volume plus the CO2 that is generated or degenerated within the control volume. So if you have a chemical reaction that creates CO2 out of other chemical reagents, this could be this additional S term. If you take now a closer look on this equation here, you will probably, at least if you have seen the video about heat transfer, really remember this form, which is typical for heat and diffusion transfer. Because if we come back to the heat diffusion equation, you can see that it's basically the same, except that now in case of the temperature, in case of the diffusion, the concentration is driving instead of the temperature for the heat diffusion equation. But on the right-hand side, you have the fluxes that are leaving your control volume plus a sink or source term. The heat transfer and the diffusion equation also resemble the Navier-Stokes equation. I don't want to go into detail this time. I'd already described it in the heat transfer video. But always keep in mind that all these equations have a very similar form. And this will help you later on if in the simulation part, because you can use similar mathematical concepts to solve these equations. And this means if you have understand how to solve a diffusion problem or the Navier-Stokes equation in a simplified version, you will also be able to solve the heat diffusion equation because it has the same roots. So let's quickly summarize what we've learned in this section of the lecture. So at the start, I said that you should be able to name the governing equations of diffusion. And here you should understand what the diffusion coefficient is, what it depends of in case of gases or liquids. And obviously you should also be able to understand and name fixed laws. You should also be able to solve simplified diffusion problems. And this is something that we are going to do in the lecture with a short example. But basically it's the same as you did for the heat transfer. So you will have a closer look at the control volume and just see where the flux is moving, if it's moving inside or outside of the control volume. And then you will end up with a set of equations that you have to solve. Thank you for your attention and see you in the lecture.